As we discussed in the training module, four-stroke engine construction, the pistons, valves, and cylinders work together to first draw air and fuel into the cylinder and then expels combustion gases into the exhaust system. While some descriptions of this movement states that vacuum draws air into the cylinder, it is more accurate to state that pressure moves air into the cylinder. During engine operation, these components act as an air pump, constantly moving air from the intake side to the exhaust side. Engines at rest have equal pressure at all points in the intake, cylinder, and exhaust. The weight of the atmosphere creates this pressure and is measured in inches of mercury. Atmospheric pressure is about 30 inches of mercury at sea level and drops as altitude increases. This pressure change does affect engine performance. For instance, when driving on some mountaintops, atmospheric pressure can be as low as 20 inches of mercury. After starting an engine, internal pressures change based on the test location, engine speed, and throttle position. This example looks at a normal aspirated engine, but the principles that move air through the engine also hold true for forced induction engines. As the piston descends on the intake stroke, cylinder volume increases. This reduces pressure in the cylinder, allowing the higher intake manifold pressure to push air and fuel into the cylinder. Burned gases exit the cylinder due to the same forces. As the piston moves up, cylinder volume decreases, increasing cylinder pressure. This higher pressure moves exhaust gases into the exhaust manifold. The intake system includes several potential restrictions, which can reduce manifold pressure. The air filter and intake piping may cause resistance, slightly decreasing manifold pressure. In addition, gasoline engines and a few diesels include a throttle plate, which can greatly reduce intake manifold pressure. When a throttle plate closes, the engine pumps air out faster than the throttle plate allows air into the intake manifold. Since there is less air in a fixed volume, intake manifold pressure drops. This occurs at idle and during deceleration. The pressure reaches its lowest point with the throttle plate closed and high engine RPM. During acceleration or when climbing a hill, engine load requires large throttle openings. Under these conditions, intake manifold pressure moves up, approaching atmospheric pressure. Cylinder pressure can greatly exceed atmospheric pressure. While the cylinder starts with air slightly below manifold pressure, the compression stroke reduces cylinder volume, greatly increasing pressure. During the power stroke, combustion events also increase cylinder pressure. Since pressures outside of the combustion chamber are much lower, gases in the combustion chamber leak, typically past the piston ring. We call these gases entering the engine crankcase blow-by. If the crankcase were sealed, this additional pressure would blow out seals, creating oil leaks at the sealing surface. To reduce blow-by pressure, the intake system includes a positive crankcase ventilation system. The system includes a fresh air intake for the crankcase, along with a tube and valve to draw crankcase gases into the intake manifold. The system draws blow-by gases and other contaminants out of the crankcase and burns them in the combustion chamber. The exhaust manifold does not have a throttle plate, so any pressure present in the system quickly returns to atmospheric pressure. Some exhaust pressure occurs due to muffler or catalytic converter restrictions, but should not be more than 1 or 2 psi. Any blockage in the exhaust system will prevent exhaust from escaping, greatly increasing exhaust pressure. In order for the engine to idle, enough air must flow past the throttle to support engine operation. Until recently, a special passageway provided idle air. The passage included an adjusting screw or an electronically controlled valve, which allowed enough air into the manifold to maintain the desired RPM. On vehicles with the electronic throttle control system, the throttle position motor opens the throttle plate itself to provide idle air. The PCM monitors and controls the throttle plate to maintain the correct idle speed. Total idle airflow varies with engine conditions. During cold engine operation, the idle control system allows more air into the engine, increasing idle speed. As the engine warms up, the PCM reduces the amount of idle air until the engine reaches normal temperature and idle speed. Each cylinder in the engine is an air pump sharing a common intake and exhaust manifold with the other cylinders. Because of this, the action of each cylinder creates pressure pulses in the manifolds as valves snap open and closed. In addition, the intake and exhaust valves may open simultaneously, allowing the pressure pulses from the intake and exhaust to interact with each other. Engineers can tune the engine to take advantage of these pressure pulses. Designers modify intake manifold shape, valve timing, and exhaust manifolds to improve airflow in the engine. Since pressure pulse timing changes with engine RPM, a given intake manifold design targets a specific RPM range and may not work under all engine RPM ranges. On some models, engineers add resonance chambers to the manifold that help increase the tuned RPM range. On other engines, a valve in the intake modifies runner length, providing two separate intake manifold configurations, one for a low-speed operation and another for high RPM. Many different problems can affect engine pumping and cylinder performance. In this section, we will look at these problems starting at the intake, moving through the cylinder, and ending at the exhaust system. Dirty air filters represent the most common intake fault. When dirt plugs the air filter, it decreases airflow. Problems with the throttle or idle air control system can affect intake manifold pressures. Poorly adjusted idle air screws or component failures can allow incorrect airflow, leading to high or low idle speeds, stalling, or DTCs. Air leaks in hoses or intake manifold gaskets can also affect engine operation, increasing idle speeds or setting DTCs. We refer to this as unmetered air because it bypasses the air intake system. On engines with a MAF sensor, this unmetered air will not match the sensor reading, while adding unmetered air to MAP-equipped engines will increase the idle speed. Cam timing problems can also affect intake manifold pressure. When cam timing changes, efficiency drops, increasing intake manifold pressure. Cylinder conditions can also affect engine pumping. When piston rings wear, cylinder gas leaks past the rings down the cylinder wall. This increases engine blow-by and overloads the positive crankcase ventilation system. When this happens, crankcase gases backflow through the crankcase vent intake, fouling the intake and throttle body with engine oil. If the valves do not properly seal, the piston pushes air back into the intake manifold. This can affect the air-fuel ratio, causing the PCM to set a rich mixture DTC. The final fault occurs during exhaust system blockages. Exhaust system restrictions occur when impacts crush the exhaust pipe or damage the catalytic converter. In some cases, a blow to the catalytic converter can shatter the substrate and plug the converter outlet. Anytime blockage occurs, exhaust system pressures increase and the engine cannot pump air. When troubleshooting cylinder performance problems, three tools provide critical troubleshooting information. Compression testers and cylinder leak-down testers evaluate internal cylinder condition, while vacuum gauges use intake manifold pressure to identify other problems affecting the engine's ability to pump air. Whenever you evaluate cylinder performance, begin by warming the engine to normal operating temperature. Use the cooling fans to identify a warm engine. Once the cooling fans have cycled twice, the engine is ready for testing. Warming the engine ensures all metal components are fully expanded and that the idle control system is targeting normal engine RPM. To evaluate cylinder condition, a compression tester provides a quick check of overall cylinder condition. To use the tool, first disable the fuel delivery and ignition system, and then remove all the spark plugs. Install the compression tester in the first cylinder to be tested and fully open the throttle. Note: to open the throttle on engines with an electronically controlled throttle, turn the key to key on, engine off, and fully depress the accelerator pedal. These steps command the electronic throttle control system to open the throttle fully. During a compression check, the starter motor turns the crankshaft over and the cylinder pushes air into the compression tester. A check valve at the bottom of the compression tester holds pressure from each compression stroke, and after 6 to 10 compression strokes, the compression tester will display the maximum compression reading. Once you've tested all cylinders, compare the results cylinder by cylinder. If the highest and lowest pressures are more than 10% apart, further checks are required. Compression failures may be caused by leaking valves, piston rings, or a bad head gasket. To isolate which fault is present, use a cylinder leak-down tester. Most leak-down testers include a gauge reading the regulated pressure and a gauge showing cylinder leak-down. When the regulated pressure is set to 100 psi, the pressure difference between the two gauges is the leakage percentage. In this example, the first gauge reads 100 psi, and the second gauge reads 88 psi. Calculating the difference between the gauges, leakage is 12%. Some testers have a single gauge which must be set to 100 psi, or 100%, with the hose disconnected prior to use. To use the tool, connect the tool to the cylinder and subtract the gauge reading from 100 to calculate the leak-down percentage. Prior to leak-down testing, be sure to place the cylinder at top dead center of the compression stroke. With the connecting rod perfectly vertical, air pressure applied by the tester cannot rotate the crankshaft. If the connecting rod has any angle, the pressure will rotate the cylinder and you'll need to start over. If you connect the leak-down tester to the cylinder using the same hose as the compression tester, be sure to remove the check valve from the hose connection. If you forget and leave the valve in, both gauges will show 100 psi during testing. When testing a cylinder with a high leakage percentage, listen for air leaking past the valves or rings. If the rings allow air past the piston rings, you can hear air leaking out of the dipstick tube or the oil fill cap. If the air is leaking past the intake valve, you will hear air flowing out of the intake manifold. For leaks out of the exhaust valve, air will exit the tailpipe. When the leak is at the head gasket, air from the leak-down tester will bubble out of the radiator. A vacuum gauge measures manifold pressure. If the gauge reads 0, manifold pressure is equal to atmospheric pressure. At sea level, a typical engine in good condition shows a steady vacuum reading of 20.5 to 21.5 inches of mercury at idle. Like any vehicle problem, a vehicle inspection can provide clues to fuel trim codes or manifold pressure problems. During a visual inspection, check for aftermarket intake assemblies, crushed or damaged exhaust systems, and leaking or disconnected vacuum hoses. To check for intake manifold leaks, spray throttle body cleaner along manifold mating surfaces with the engine running. If the engine RPM changes, you've identified the problem. This concludes the module on engine pumping theory. An understanding of engine pumping theory, along with typical vacuum and compression readings, will allow you to identify internal engine faults without disassembling the engine.